So this is our last presentation today. Every other presentation up to here has been full of great data and I feel paints a large, broad picture. This presentation, maybe it's because we're grappling with some things right now we want your feedback on, but it's going to be more specific to some of the challenges we're encountering right now in our research in one model. So while it might be broader in a sense, it's also a lot more narrow. So bear with me and feel free to, I guess we're using this as a bit as an opportunity that we can learn from you beyond even what we've learned from you already today. So I'm going to be talking about modeling soil P, and a lot of what I have is building right on what Peter just spoke about. So this is going to be a case study focusing on the SWAT model and ongoing research in our group. So I've included Gray and Becca on this presentation, and we might have to ask some of your questions to Gray if they get too technical, because he's been doing a lot of the SWAT simulations since he joined our group in April. My outline is just 5 questions that I felt like I wanted to, just share with you guys today where we're thinking about with these. So the first is, why do we care? And maybe it's, why is our group here even speaking? The second is, why might we be using the SWAT model to be dealing with issues pertaining to today's talks? The third is, something that comes up a lot is, can SWAT be used at the field scale? And maybe more broadly, is SWAT an applicable model for thinking about farm actions and things like soil test phosphorus, which is measured, we've already been mentioned today, like within field zones. So is SWAT even the right tool to be using for that? And I don't necessarily have yeses and nos for these. Just these are questions we're asking. Fourth, can soil test phosphorus be input in SWAT? We've just heard from Peter that it can, but we'll discuss some of the issues we're coming across and hopefully get some feedback about where we might go with trying to tie together some sort of loose ends in the model. And then the fifth is other challenges or opportunities we're thinking about, along with conclusions. So this should be shorter than the other presentations. Why are we here today? Why are we working on this issue? I'm not a phosphorus chemistry expert, but we've been using the SWAT model for many years in different stakeholder-driven scenario analysis environments in Northwest Ohio and in some of the adjacent states. And stakeholders have continually come back to us with certain requests or concerns or disappointment that the model's not doing certain things. So some of these are around inputting soil test data directly into SWAT. Some are using soil test data in scenario analysis, something that Laura mentioned earlier today, thinking about if we were to do this or that with, soil test phosphorus fields above this, what would happen? But until we can do that first one, we can't really do that second. And then the third is around simulation of manure and legacy P, which is again related to soil test P, but then also more broadly to some of the things we were just talking about, is the architecture of the model really able to capture what's happening with manure, for instance. There are additional concerns we've been coming up across the last couple of years in this modeling, which we're going to continue talking about today, and that is the need to reduce the labile P to very low or unrealistically low values for 2 purposes. One is calibration of reach level phosphorus loading. When we, in the last several years, calibrating, and this is in the Maumee watershed where we've been doing a lot of our talk today, but when we've been calibrating our model, we've been finding that that labile P has to be brought to a very low value before the reach level Drp reduces to the level where it's at in reality. So maybe that wasn't the real issue. Maybe it's something else, but we've been doing a lot of calibrating and a lot of thinking, and that seemed to be something that we've been determining for several years. And the second has to do with the crop growth sensitivity to the phosphorus fertilizers applied. We'll be talking a little bit more about that in this presentation. So where we're at right now is we're using a very perhaps unrealistically low labile pronunciation p-value in our model, which we've just been hearing about could be problematic. So let's go through the questions. Why would we be thinking about using the soil and water assessment tool in relation to soil test phosphorus or phosphorus cycling? So SWAT estimates discharge nutrients and sediments from the field to the watershed outlet. It's commonly used in this region and globally to estimate the impacts of farm conservation at the watershed scale, or farm conservation or just farming practices at the watershed scale. Lots of knobs you can turn and inputs that you can put in for farm operations. It's also used, there are other uses like climate change, testing climate change, influence on hydrology, or testing land use change and cropping patterns. And there's other practical reasons, like a lot of people are using this model. The code is open source, so we can make changes. There is some support through ARS. In this country, we have data that we can put into this model. So these are some of the reasons we're using SWAT in our research group, and why many are using this model for these types of projects. A little bit about the SWAT model. For those, most of you know a lot about SWAT, but a few of you might know nothing. So I tried to get a little bit in here about what is SWAT. So the SWAT model simulates climate, land use, and land management actions. You have, when we talk about the model, sometimes we're talking about, or especially with limitations, we might be talking about inputs to the model, like limitations of data to put in. And like, we don't know what the farmer's doing on field X, that's an input limitation. Or sometimes the limitation is the model just doesn't simulate something at all, or sometimes it's we can't actually test that it's working because we don't have data on the other end for calibration or validation of a routine. So there are different types of, many different types of modeling decisions, and the process, I guess, right here I have written here that it's a complicated model with many decisions, inputs, and parameters. So the process of setting up and calibrating, inputting data to calibrating and using a SWAT model has uncertainty at many scales, including how you choose to set the model up spatially, which within the model there's actually lots of models you can turn on and off. So as mentioned, there's more than one soil phosphorus model, so an old one and a new one. So that's the same thing with carbon. There's multiple models you can turn on or off, or water table algorithms within it. So it's like a model of models. So you have to choose which models to use, and then there are certain inputs that you have at the field scale or farm scale. Land management is included really in those inputs, but often we don't have data in the same way to support our decisions about what to do with land management at a large watershed. So we're making decisions based on talking with crop advisors or knowing something about farm surveys. Parameterization is important in the calibration of the model, getting it so that it's predicting well, and it's a highly parameterized model, which is sometimes problematic. And then measured data is needed for calibration of the model. Hopefully that gives enough background that you feel like you can kind of follow where this fits in. A little bit broader, where does this fit in, and what have we been doing the last few years? So we've been looking at the Maumee River watershed, and many other modeling groups are doing the same thing. So REM from Heidelberg has a model of the Maumee, or many models of the Maumee River watershed. And so what we've done recently is to try to deal with some of the uncertainty from many different sources of uncertainty in the modeling process, is compare multiple models to one another to see how they're predicting, and to see what the future might be for guiding policy about conservation actions in the Maumee River watershed. And so this is just a paper and a project there, and that this work is continued, and we're coming out with the next round of those projects papers will, before too long, hopefully be submitted for publication. All right. I just wanted to say just a couple more things about our use of SWAT and potential use of SWAT, because I've been hearing for several years now a dominant argument that people make that SWAT is not a field scale model, and I think that comes from the fact that historically the model, or if you use the default setup in ArcGIS or ArcSWAT, you end up with, if this is the ortho imagery, you would end up with hydrologic response units, or HRUs, which is the smallest unit in the model, set up within a subbasin. They would be just lumped based on common soil type, land use, and slope. And so you wouldn't necessarily be simulating farmer X's field. You would be simulating some little bit of lots of fields within a watershed. And that's been a little bit problematic. It's hydrologically, it makes sense because those units act together, but it doesn't make sense for management. And so what we've been doing now for several years, and others have been doing before us, Tammy Vieth's group, Margaret Gatow, is setting up SWAT at more of a field scale, and it might mean different things to different groups. Tammy Vieth's work has been like with sub-field units at a very small watershed scale. This that I'm showing you here is the whole Maumee River watershed, and the farm fields are probably bigger than the actual fields. You can see there are many times where you have, in one field, you have multiple, what looks like multiple units, but this is getting closer to the field scale for our spatial units, and it's using common rotations over 7 years to determine what is a field and dividing by roads and all of that. So I would argue that when it comes to inputs to the model, you can input, if you set up the model the right way, you could input farm scale or field scale inputs to a model and get outputs at the field scale. What still you might argue is lacking is that what are these fields don't interact with one another in the current SWAT model, and that will be when eventually SWAT Plus comes out. That's the newest version of SWAT that's been under development for a few years now. They will have landscape routing that will hopefully facilitate that. So maybe I didn't need to make that point, but I think when we talk about why do you even use a model like this for thinking about farm level actions, it's important to keep in the context of farm level actions being applicable in that model. A little bit more about the HRU. If we want to, instead of thinking across space horizontally, thinking vertically, which is really what we're talking about with a lot of the soil processes, SWAT has land management actions up here, and then it has soil horizons. These soil horizons are broken up based on Surgo soil data, or you could use SATSCO, but Surgo soil data has different depths for soil layers, and then all these attributes that just get populated in the model from Surgo soil. Then additionally, we can put in tile drains or subsurface drains in the model at a certain elevation or a depth. Impervious, there's an impervious layer that you tell SWAT what depth that should be at for a field. Then there's aquifers, and that's the basic vertical structure of the model. The next question is, can soil test phosphorus be input in SWAT? So let's start with talking about phosphorus simulation from the HRU or the field to the reach or river. So here I'm just showing the names in SWAT of the different I guess these are the pools of phosphorus, but also the pathways. And then, so this is in the HRU. We have our active, stable, fresh, etc. But then when we're exporting, this is the language that SWAT uses. And then in the reach, this is the language. And so we don't have to belabor the point, but nomenclature has been confusing in this model for many years. For instance, solution P becomes soluble P becomes mineral P, depending on where you're looking at it. And sediment and organic P exported from an HRU just go into the organic P fraction in the reach. There's no sediment P fraction. And then once it gets to the reach, sediment and phosphorus basically don't interact, which is not realistic either. So there are some limitations in the reach, but we're focusing mainly here on, I think, up in the watershed, up in the farm fields. SWAT does have a tile phosphorus fraction that goes through subsurface drains, and we have questions about it that we could talk about over dinner or whatever, but there's some oddities in that routine as well. And so one of the questions I put on the board is how much of, and maybe Kevin, you have some ideas about this, but how much of your tile phosphorus comes through macropore flow versus just sort of like a slow leaching or anyway, but to get an idea of if the model's doing some of these things correctly. So that's a bit broader, but then if we go into the pools, which we were just looking at with Peter's talk, these are the different pools, and how are these working in SWAT? So initialization of these, again, this is some summary of the previous talk, but we've got our phosphorus availability index, which initializes some of the pools. The solution P or labile P is the term when you initialize it, but it becomes solution P, that we specify in the model input file. So that's where the soil test phosphorus sort of makes the most sense for a plug-in, we think. But then initialize with organic carbon on the organic size. So from the last presentation and talking with Peter, yes, we can simulate soil test phosphorus as an input to SWAT by using the sort of rule of thumb, solution P equals soil test P times 0.5. That would be plugging it in here in the initialization. If we do that, that is different than what we've been doing in the model for some time. So we want to show you some of the output we're getting, and maybe you'll have some seeds of ideas to help us with this approach. So if we take one example HRU from our model because we wanted to show just one field, it gets complicated when we're showing all those fields and their results. This HRU has a corn-soybean rotation, tile drains, hydrologic soil group C, 1% organic carbon content, 25 to 40% clay, depending on what layer you're in. Did I unplug something important? I'm not sure what that is. Maybe that's just a power cord. Okay. And then phosphorus fertilizer applications of about 26 kilogram per hectare per year. So that's our HRU. And then this is just what the soil layers, so the very top is the 1 centimeter surface, then 18, 61, 1 meter we have tile drains, 1.2 we have the impervious layer, 1.5 soil horizon 3 ends, and then shallow aquifer and deep aquifer. So that's our HRU. And here are some graphs, and if you feel you're not following them fully, that's okay. We wanted to put some data in front of you to think about this problem. So this is the phosphorus cycle simulation by horizon. So we have our depths, our first, second, third, and fourth horizon, with solution P, using the rule of thumb. So then our STP would be about 50, so we have labile P of 25. We have the following dynamics happening. So on the left, we have our mineral P, and on the right, we have our organic P fractions. We have stable in blue, active in green, solution in red, and over there, the teal is organic P, and the purple is the fresh organic P. I think, yeah, this is the only graph we have like this one. But I think this is promising at the first glance. This is over many years, 30 years or 40 years. So that's what the little up and down, it's like yearly cycles. So at first glance, what we're seeing in the top two soil layers is what looks like fairly stable pools. And that's about as far as I can go in my analysis because I'm not a soil phosphorus expert. So the good thing is it looks like with fertilization at about crop requirements, our pools aren't changing drastically. They're staying in some sort of equilibrium. What's more troubling is when we look at crop yield. So this top one here, now this is actually all for soil layer. Sorry, this is crop yield, and then these are soil horizon 2. So crop yields over those 40 years, you only see one line here because corn with phosphorus fertilizer is blue and without is orange, and they're both on the same thing. So we have no crop yield decline simulated in the model when we apply no phosphorus fertilizer for 40 years when we set STP at about 50 Bray P1. So we would expect that we would have a crop yield decline earlier. What else are we seeing? So here, the second panel is solution P in that horizon. And when we don't apply phosphorus fertilizer, solution P starts to, by the end of the simulation, approach 0 milligram per kilogram. And then we have our total P and our Bray P1, like our STP estimate, which is just 2 times solution P. So we would expect, I think, that under an STP 50 condition, we would see a crop yield decrease within 40 years. But even if maybe STP 50 is too high, so we went down, thought I had a 20 in here. I might have deleted that slide by accident. Oops. But we have these results for STP 20. And I'm not sure why it's not there. I think I deleted it thinking it was the same as this one. So this one is STP 2, which is really low. So any field that has an soil test value of 2 probably would be feeling some crop stress if you didn't apply phosphorus fertilizer. So here it takes 32 years before we have any difference in our crop yields. I don't know that there's a whole lot else to say about these pools other than if you know how these pools should work and you're looking at them and you see something that looks funny, you tell us. But we are seeing that some of the pools are rising, which under the fertilization condition, which would indicate that that STP value that we gave it really was a little too low, and that if we were to maintain crop production, it would be with fertilizer, we'd be raising it a little bit. But I mean, from my standpoint as a modeler, I'm not seeing anything that tells me that STP 50 was better than STP 2 in these two, other than with the rule of thumb, STP 2 is way off, or labile of 1, STP 2 is way off. Okay, so I can say even less about this graphic. We're still trying to figure out what's going on here. But over 1 year of simulation, so that now we're just looking at 1 year, we're wondering why crop growth isn't limited by low solution P. So what we have plotted here is now the orange is the maximum phosphorus uptake that could take place from a soil layer, and the blue is the actual phosphorus uptake from that soil layer by day. And so for the first horizon, we're always meeting our crop need, and the second, we're pretty much always able to uptake, the plant's able to uptake what it needs from the soil. And then horizon 3 and 4, I understand a little bit less, but it may be because of where the impermeable layer is that we're not actually accessing those very much. So there's a little more data for those that might understand the plant dynamics better than me. If you have some ideas, we can talk about later. The last thing I want to show about results is the DRP exports. So again, the issue isn't just the sensitivity of the crops, but we're having trouble calibrating the model when we have soil test phosphorus in the right range. Again, there's many things that knobs we should be turning differently to get that calibration. But I thought we would throw up a little bit of data for those that might have a perspective on this. So when we set soil test phosphorus to the 50 value, over 1 year of simulation, we saw solution P exported from this HRU of and surface runoff about 0.6 kilograms per hectare per year when we fertilized. And then the DRP was 0.12 kilograms per hectare in that year. And we're wondering, is that reasonable? From some of the things we heard earlier today, I remember something about a 0.3 from Kevin's talk. I think what's not reasonable is that the DRP in the tiles is so much lower than in surface runoff, and we've been driving that down actually to try to calibrate the model, because if we have, I forget what you said, Kevin, but it was more DRP coming through tiles than through surface, and if we did that, then we would be at more than 1.2 kilograms per hectare per year. So how do we get the surface runoff DRP down to where it should be if we have our labile P or solution P set at 50 is, I guess, the question about this one. So other challenges and opportunities as well as the conclusions. I might just start with the conclusions because that's what we've just been talking through. Something is wrong in SWAT simulation of crop phosphorus stress, we think, under low soil P conditions. So what do we do to fix that? Is it a problem of not having a true solution phosphorus pool in the model? Or is it a problem with the relation, like we talked in Peter's talk about how long it takes for the soil to deliver more solution P when it's needed from the active pool. So is that happening too fast? Should we be seeing, crop stress because it uses up the solution pool and, needs more? I think there's too much in the solution pool as it's currently set. And so we could talk more about that. There are a lot of other things that we could do to improve SWAT simulation of the soil, which gets to some of these other challenges. So from Laura's talk, stratification, phosphorus in a no-till system, I have a couple slides if you want to look at it, but we are seeing that when you use no-till in the model, we have increases in phosphorus concentrations in those top soil layers. The relation of soil phosphorus to soil carbon, and really soil carbon itself in the model is, we found problems with both soil carbon routines 1 and 2, and soil carbon routine 0, which is the default, doesn't do anything with carbon beyond initialization. So we're trying to figure out some issues, but at the same time, are we getting the soil phosphorus and carbon related to one another properly? The nomenclature around phosphorus and SWAT, pH controlling phosphorus availability. There is some indicator that pH is in the model, but I don't think it's really doing anything right now. And so if we could get that, hooked up and working in the model, that might be relevant. The streambed simulation was mentioned. I mentioned that right now it's, phosphorus and sediment are not related to one another once they reach the stream. Better simulating manure and inorganic slow release fertilizers. maybe gets more to what you were talking about, Peter, a little bit, and then capturing within field variability of P and thinking about also how we set up the model and what our spatial units are. Those are some of the thoughts I had about our specific modeling that we're doing in our world and how it relates to all of this, and I realize that's rather specific. I hope that it stimulates a little bit of discussion around potential barriers or opportunities that we could have for improving phosphorus modeling in SWAT or similar models. So, thanks.